So, good afternoon, everybody. So I'm Jeff Eckeld from GE Oil and Gas, and most of you are aware, I'm sure, that Wellstream Flexibles was acquired by GE a couple of years ago, and the MAPS business was a close follower. We became a GE acquisition maybe 3 or 4 months after the Wellstream business was acquired. So I'm going to say a couple of slides just on the GE sort of technology development program, you know what drives it and what focuses on, and I've got one slide on some Wellstream activity there. And then I'm going to focus the rest of the presentation on a particular technology, which, if you like, has been part of that. Clearly, it preceded the GE process, but it's been part of the GE process since then and popped out the other side. And although the technology is sort of generic, it has a particular application for the integrity management of flexible pipe. And those of you that were at the DNV meeting the other week also goes some way to start to answer the unknown unknowns, which is a phrase that was used a lot last week, only been used once so far today. So maybe things have moved on in the 2 weeks. Just I say a little bit on the GE Oil and Gas process. GE is a large company, you know. It has sort of common processes across the company, irrespective of to whether you're in the oil and gas business or healthcare or whatever, but that provides a certain discipline. You know, GE is many things, depending on whether you've got a refrigerator or what your experience is and that sort of thing. But for sure, it prides itself on technology innovation. It believes that certainly these days that if you're not in the technology game, you're not going to be long on this planet as an operating concern. So it has, you know, a structured process which, you know, starts with sort of blue skies. And, you know, within GE, we have what's called the research centers in Munich and in China and in New York and now in Brazil, which is sort of generates the ideas and sort of brings them to, you know, a period of sort of scientific feasibility. And then, you know, once it gets into the P&Ls, you know, the business units, it goes from new technology introduction. So that's not a product, that's in terms of taking the technology and, you know, can we make it work in the context of our business? A new product is, as the name suggests, that's taking it, you know, that sort of fully formed idea and converting it into something which is marketable, saleable, and adds value to the business. And so, you know, each sort of idea sort of goes through that sort of process, and there's sort of quite a rigorous assessment, you know, gates as you'd expect, both for, you know, commercial feasibility, but importantly for technical feasibility, i.e., does it work? You know, so those questions are asked all the time, because at the end of the day, GE is putting its name on the products and the services which are being made available. And just to illustrate the sort of tollgate process, and this sort of aligns with that which is in the API in terms of 0 to 7 and tollgate 8 here, and that's where you've got a field-proven sort of solution which is available to be sold and you know, as a commercial proposition. So, you know, there's a series of steps, and one of the benefits of, you know, being a GE company is that you do have access not just to the process, but if you've got a good idea to the capital to take it forward. And Wellstream is no exception. You know, consolidating its product portfolio, taking new ideas through the process is something which is, you know, very exciting in the company at the moment, and you know, make quite good progress. And you know, all that's been possible in the last couple of years as the company's gone from a PLC, where you've got you know, the owners have certain motivations, to, you know, being a bit of a big corporate company with technology at its heart. So that's sort of it in a nutshell in terms of the process. I'm going to say a little bit about this particular technology, and thank you to Jan for mentioning it in his presentation. MAPS is both a trade name and an acronym. And to give you a clue, M is magnetic, P is permeability, S stands for system, I'll give you that. I'll give Jan a prize if he can work that out by the time I'm finished. Okay, so I've got one slide on what the technology does, and then I'll just flip straight into what we're doing for flexible pipe. So what we do is we measure stress. So M is magnetic, it's a magnetic technique, we measure stress on ferromagnetic materials. So a magnet needs to stick to it. And it's an absolute measure. And we deliver megapascals from that absolute measure. So if you've got residuals, we heard about residuals this morning, and if you've got external stress, we provide the total. For specific applications, we can separate residuals from the externally applied stress, but that's a domain-specific thoughts you need to put into that. But we deliver the total stress. If you do certain things with a probe, we can deliver the biaxial stress distribution in the plane. If you do other things with a probe, we can measure through the thickness. Accuracy, question always somebody asks, and I always reply, it depends. It depends on the steel. It depends how much work we put into understanding the steel to be able to provide the stress measurement. It's a model technique. It's underpinned by physics. It's not empirical. I mean, just to illustrate, you probably can't see, but this is a blind trial where we compared with strain gauges. Obviously, the strain gauge is a relative technique, and we delivered on each point 2 absolute measures, before and after. And this is a blind trial in that we hadn't seen the piece of steel before. We did our measurements and provided those, and somebody else did the comparison. This was done for Messier Doughty, who provide the landing gear on at least 50% of the civil aircraft that we would have flown in to get to Stavanger. Goodrich supplied the landing gear to the other 50%. And a few things which are useful with a magnetic technique is that you don't have to touch. There's nothing in contact with it. We can stand off from the surface. And that's particularly valuable for flexible pipe because we're talking about being able to stand off the armor wires and sensing through the polymer shield. So there's no intervention within the structure. As long as the gap is between our probe and the part we're measuring is not ferromagnetic, it's sort of transparent. So whether it's water, air, aluminium, epoxy coatings, or whatever. And it's possible, you can think of it as a highly quantified, low-frequency eddy current technique in terms of its physics, a kilohertz or so. That allows us to do static measurements clearly, but also we can do measurements at some speed. So that's the sort of technology. It's magnetic. Permeability, we actually measure the magnetic characteristics of the part of the material, and underneath the hood is the sort of the physics to be able to relate changes in those magnetic properties to the stress that we as engineers understand in terms of megapascals. So flexible pipe. Now, measuring on a piece of flat steel like this, semi-infinite plate, that's easy. For flexible pipe, it isn't easy. In fact, it isn't round is not helpful, but the bigger problem is, of course, it's an unbonded structure with lots of steel elements within it. And the coupling, our probe is essentially a C-core, and there are sensors around the C-core. The flux couples with all of the layers within the structure. And so we need to have an understanding of how the if you like, the magnetic flux interacts with all those layers to be able to make sense of it. It certainly couples with the tensile armor wires, couples with the pressure armor wire layer, and if the carcass was ferromagnetic, we would couple with that. 316 is not ferromagnetic. And so, as I say, we have that sort of coupling which we need to unpick, but also particular challenges are that the tensile armor wire layers are laid down in the manufacturing process. The spacing isn't uniform and it's unknown. That spacing might change to an unknown degree because of the way the riser moves in service. The wires may touch or be touching, and that may change depending on what the pipe might be doing in service. They might touch under your probe. They might touch at a distance from probe. So all of that plays havoc with your magnetic circuit. And what's worse is that you have no knowledge of what's happening because you've got the polymer sheath on the outside. So it's taken a lot of time to unpick all of that. And to be frank, if we were not part of GE, we wouldn't have been able to do it because within GE we've been able to piggyback on pipe qualification tests and have lots of samples. More samples, fill this room of material that we've been able to do measurements of so that we can actually understand that and be able to compensate for these effects. I'll say residual stress in wires has been mentioned this morning. I'll say a bit more about that later. So that's the sort of challenge. And the sort of notion is that you have a series of probes if you have a monitor, because you need to pick up all the wires. The idea is we pick up and sense the stress in the wires. So if you have a static device, you need more than one probe to pick up all the wires. For an inspection device, you can have just one probe, which itself scans around or along the helix length to pick up what's happening in all the wires. And so this is just a visualization of the equipment, and I'll got some real pictures in a minute. What we found is the sort of response in the context of the MAPS technology is independent of the OEM. Certainly our early work was done with non-GE pipe. And part of the proposition is measurement of wire breaks. One of the other neat things about this application is the fact that the flexible pipe are an unbonded structure. And so if you've got a wire break, the stress at the position of the break is 0. And we can measure that either absolutely or by comparing it with its neighbors or by comparing it with time. But because it's unbonded, there's a distance over which that stress is picked up through friction. And so we could detect the position of a wire break a distance away from the location of the break. So if you've got challenges with an I-tube structures where you haven't got access for inspection, visual or otherwise, there's a potential to be able to put a piece of equipment remote from that restricted area and sense underneath bend stiffeners, I-tubes, and the like. So what I'll be able to show you is picking up breaks to the individual wire and also the inner and outer wire layers. Certainly for the tensile armor wire layers, we see the pressure armor wire layers, but we can't quantify that effect just now. And the other point to make on this general slide is that it's not a pingometer. We're not reliant on a transient response. If you've got a wire break or an effect which causes a wire break, it leaves a lasting impression in the stress distribution, which we can pick up. So just to sort of step back from that and just think about it in the context of trying to understand riser behaviors, because flexible pipe, I mean, one of the themes of this morning and certainly last week is people beginning to scratch their heads that this pipe is really rather more complicated than we first thought. It's just not a simple load share between layers, and lots of things happening, and they're not second order anymore. Some of these things which we assumed were second order were perhaps coming to affect integrity certainly 15 and 20 years in. So what we've got a few slides here just showing how we're using the technology, for example, within a pipe qualification program to actually try to understand a little bit more about what's happening within the pipe when it's under load. So just to illustrate, this is a device. This is actually a device on a tension test. This happens to be located in Porto Alegre in Brazil, able to communicate it remotely into our office in Oxfordshire in the UK. It happens to be strain gauged. This is sort of the MAPS response which we get, which is sort of mirrors the strain gauge result. Number of probes for a static device, the number of probes depends on the number of wires and the diameter, clearly. Within each probe are a number of sensors. So there's about 100% redundancy in terms of physical sensing of the wires that would strictly be necessary for the number of wires in the structure. So looking at the results in a particular way, FT1 is the inner wire layer, tensile armor. FT2 is the outer. This is armor number, wire number rather, and this is time. And here we have a load trace, and the total load trace is with a tension which is constant, and then there's an upset, if you like, and then an increase, and then the pressure is a gradual increase and then constant. And this trace here, this time period, is between these two vertical bars. So this is constant load. So what we're doing is picking up what's happening in individual layers, in the individual wires, as you apply a constant load. And of course, if you do a very simple calculation, you would think that everything's uniformly distributed, and because that's what my analysis says and all that sort of thing. But the reality is that the manufacture process is fantastic, really, if you look at it. And if you haven't seen it, take the opportunity to do so. I mean, if you remember the Thunderbirds cartoon program, the equipment is a bit like that. It's fascinating to watch if you're an engineer. But the wires go through a very tough time even before it sees a pipe. And so basic assumptions may well be brought to your attention that not all the wires are loaded equally at the same time. Maybe there's a bit of a time constant, not just between the layers, but within the pipe. We heard a bit about that this morning. For sure, wires are, the steel is the time constant's very fast. We put a load on it, it responds very quickly. Polymers are different. And in this pipe where you've got polymer layers, you've got friction, perhaps things are a bit more complicated than your analysis would expect. So what you have here is uniform load. The two layers get to the same spot eventually, but there's a time constant and a variability across the structure before you get to there. Just moving on, this is between these 2 points, so it's constant load, and clearly nothing much happens, so that's as you'd expect, of course. And this is when we just move to the right in the time constant. Again, you've got this constant loading period, this discontinuity in axial load. You can see it if you look carefully, if you like, as a witness mark in the trace, and the load starts to pick up. But the wires take time to settle down. There's a time constant to these materials, which certainly isn't allowed in the calculation. But this is all about trying to get underneath the detail of how these materials behave, and maybe there's some thoughts that could go into this in terms of thinking about design and qualification. So looking at it another way, what happens is there's a wire break. So this is the DTR dynamic test rig in Newcastle, and in Oslo I made a slide about Newcastle weather being the same as in Oslo, and it's clearly the same as it is in Stavanger as well. So this is the pipe is in this structure. The bend stiffener is out of view. It's up here. Our device, our MAPS device, is here some 8 meters away from the work point. This is a slide wire number. This is F2, FT2, and this is time. I should have said that we have a a measure of the stress. Being engineers, you would have got that anyway. So you've got going to red is reduction in stress. And so nothing's happened in this time frame. But moving it on, what you have is at this time at about 11 in the morning, a sharp reduction in stress, which is indicative of wire break. So we find the wire break. And what you can see, this is an independent measure from the transducers on the test rig, which is a measure of the axial length of the riser section. And this oscillation is due to the movement of the riser because it's a fatigue test. And at this time, you have a discontinuity in the axial length, which corresponds to a wire break. So we've got alignment of those 2 times, and we delivered this result before we had the benefit of that. We're close to Wellstream, but not that close, if you see what I mean. Moving on in time, we can see other wire breaks, which again align with another point in here. But importantly, the point out, you can still see the original wire break. So if there's an issue around equipment not working, there's an outage or whatever, or even you're putting the equipment on after there's a wire break, you should be able to spot that. So and as I say, here you've got measures of which wire is broken. There's a forensic examination of the pipe after the event. And on this day, the measurement indicated that there were wires broken. And this is an arbitrary numbering scale for which wire. The following day, in this case, we had other wires break, and so we go on. So this was a dynamic test to destruction. And these wire breaks, the position of breaks, aligned with the forensic examination, although clearly the forensic examination only dealt with wire breaks after the event. We say we can tell which wire, but what we actually say is which wire plus or minus 1, because we don't know the wire spacing. We don't know whether the wire spacing's changed, so we put plus or minus 1 on that. That's why you've got a dark color, and then we say that's wire 28, or it could be 27 or 29, depending on because of that effect. Okay. So when a wire breaks, what happens to the stress? Well, clearly load is shed because the wire is broken, but then it's picked up elsewhere. So how does that load get picked up? Where does it get picked up? Does it track with your intuitive feel? So here we have a wire break in FT2, the outer wire layer, and you can see the wire break, so you get a stress reduction. For reasons which I still don't know, we've got the scale going the other way up here. But red is still reduction in stress. Blue is increasing tension. And if you look carefully, certainly underneath this overlay, you can see some blue, so you've got some evidence of stress and load being picked up by adjacent wires. But interestingly, in this particular load combination, and this effect will be dependent on the load combination, what you have is pickup of that load in the other layer. So much of the load change, reduction, is picked up by the other layer. And what this graph shows is over a period of time, but a snapshot, if you subtract the response of the signal between that time and this time, this is the delta. And so the red is the load loss in the outer wire layers, and the blue is a load pickup. And you have to trust me that over a period, you actually do get equilibrium. The load lost is the same as load picked up. But you know, I'm not too sure whether this would have been intuitively obvious or whether an analysis would pick this up. But you know, there's a strength to measure, and at least measure is complement to analysis. Although sometimes when you talk to analysis, you know, and you don't give them the right answer, you know, you can have challenging conversations as to which is right. But measurement is something real, something tangible. Just another graph, and I mentioned at the outset that flexible risers are really tough for us because you know, the MAPS technology relies on us being able to unpick you know, the stress signal from other things which affect the magnetic properties like microstructure, like surface quality, like temperature and all that. In fact, that's a nugget that is MAPS. But within the flexible risers, you've got all these other things happening. And one of those things is the wire moving. And I'm sure I'm annoying the cameraman by moving around. But this is actually a measure of wire movement. So, and we've got a scale on this. I think this is actually millimeters. And so in this particular increase in pressure, I think there's an increase in pressure. Again, you've got a change between the wires. Slightly complicated in that the riser section wasn't exactly straight, so you'd expect some straightening when you put load in. But hell, you know, that's important. You know, if you're doing testing and you assume your section's straight and it's not, you know, that can have impact on your results. And so if you can have an understanding of that. So what we have here is if you like, we're actually measuring. Remember, we're outside through the polymer sheath what the wires are doing, to the extent that we can put a scale on that. And so, you know, trying to provide some information into the community, certainly within GE oil and gas, in terms of how these products behave and manage. So just sort of moving on. So if you have a permanently installed system, this is this is tension. So this is the sinusoidal load. This is the MAPS result, not pure representation as a sinusoidal load, because our layer separation model is not perfect yet, but certainly good enough to predict breaks. But you know, that's not too bad. And the sort of output you can have is, you know, green is good and blue is when our equipment is working. In Brazil, they turn the power off at weekends, but you know, that's what they do. But that doesn't affect it, because you know, we can spot the wire. If a wire broke during the weekend, we'd still see it. So you know, you can have very simple outputs, or you can have more complicated outputs. Just to, in the last couple of minutes, just change tack. As I say, if you've got a permanently installed system, that's great. Monitoring load, feedback into fatigue calculations, and pick up wire breaks and all that good stuff. I mean, sometimes, you know, that's a significant commitment in terms of what you do with the data. Inspection is also an opportunity, because you know, it's not a transient measurement method. We can look for wire breaks after the factors are broken. There you can have a simpler device, a scanner, which rotates around the pipe, and that is sort of motorized and goes around the pipe under sort of a script control. Or you could actually have an axial scanner, as long as the axial distance is a pitch length. And you know, that's a typical probe. The probe is probably as big as a fist. You know, quite large in that sense. And a few things happen. we've got the things we've got to talk about, like probe liftoff and what's happening underneath the to the wires in service. But there's another confounding factor, and this comes back to this, we talked about residual stress. One thing which we're doing, we're spending quite a lot of time actually measuring the residual stress in the wires as it goes through the shop. You know, from receipt through final pipe. What happens to the residual stress distribution as it goes through the pipe? Because it's not uniform, it varies, and all of that sort of thing. And you know, that's I mean, that's great. But in terms of what we've found is, and this is irrespective of OEM, is that the residual stress distribution is actually a variable in the pipe. And in fact, the variation in residual stress as you go along a wire, or you go from wire to wire in the same pipe, is not a small number. And what we found is that that variation is comparable to the change in signal due to a wire break. So where we are at the moment, because remember, we measure the total stress. So we've got residuals and externally applied loads. What we do for an inspection currently is we need to do an inspection at 2 pressures. And so the 2 pressures, the residual stress component is constant, and so we can see the change due to the 2 pressure. We're working on means of separating the residual from the total stress, and we got the technique to do it. We've got the, if you like, the you know, the physical basis for doing it. We're just sort of working that through the system. But what we have to do, I mean, that's a scanner. This is another test rig. This is in Spade Adam in the UK. That's just a nice picture, really. But that's, if you like, the scanner as it goes around. And what we do is, and in a test rig, we can do all sorts of things, clearly. We've got different loads. And, you know, if you've got a break, the effective loading, you know, the signal is independent of the load. So that's how you spot the break. In service, clearly you can't change the tension, but you have potential to change the pressure. We have done some work, just to say that by the end of this calendar year, we hope to have done 24 risers one way or the other. What we need is access to the riser at some position, and then we can scan. Sorry, I'm pointing laser at the audience. What we can scan is, you know, distances, you know, either side of the location of the equipment. And just to wrap up, I mean, I think, you know, I talked a little bit at the beginning about the GE process and that, and what we've did on acquisition, we actually feed the technology into that process, and if you like, open it out to the rigor of that process. The original proposition was about wire break detection, you know, which is a niche in the gambit of flexible riser issues, not one we've heard about this morning particularly, but nonetheless, different operators have different issues. But you know, perhaps more fundamentally than that, what we're able to do is provide insight into how these structures are behaving in a way which, you know, doesn't affect the test result and you know provides real-time information. I say external to the riser, so we're not compromising. Our measurement technology does not compromise the test in any way. And whether it's a monitoring challenge, you're interested in something going forward, or inspection, it's something which we're able to do. And you know, it may be a unique addition, but again, it's not a panacea. It's something which adds in the armory of technologies that could be applied to help deal with the challenges of flexible pipe. Thank you.
Thank you, Jeff. Time for some questions. Any questions from the audience? Nothing? Crystal clear?
Every home should have one, by the way, you know.
Christian?
Just one of curiosity, really. Have you seen any wire breaks in the scans that you've done offshore?
Not offshore, but we've seen lots in various DTR, tension tests, pressure tests, and the like. So
yeah, that's what I understood,
yeah,
but
yeah,
I was just wondering if you've seen any real ones.
Well, there we go. Yeah, yeah. There's one in the middle here.
Any more questions?
There's a gentleman in the dead square in the middle, or unless it was already answered. Yeah.
So I can have Jan. Okay.
Go on, Trond.
I just wondered, you are part of GE Wellstream.
Yeah.
You produce flexibles as well. You show us the inspection technology here. How do you use that for? Is the results from this used in improving your flexibles?
Yes. I mean, yes. I mean, just to correct. I mean, MAPS is associated with, but not part of Wellstream in that sense. But but yes, I mean, there is this equipment is installed and being installed on all of the dynamic qualification tests around the world. So it's part and parcel of the program. You know, if and we ourselves take every opportunity to be part of any test, because trust me, I mean, when you're a little company to the side, having access to test material and large-scale testing, I mean, it's so precious. And so yeah, so we're part of that, and we're feeding into the thinking, at least, if not in the materiality of the design process, and that's really good.
Then a question from me. Check your text message about the A. I've sent it to you. It's far difficult for me to pronounce. The question is, how far away from wire breakage do you expect to pick up a significant stress change?
Okay, so that depends, and for a particular opportunity, you know, we'd have that discussion. What we can say categorically, because we've done it, we're 8 meters, not there, but 8 meters is certainly proven, and we have evidence from working with other operators that, you know, you could be up to at least twice that, and you know, that's something to talk about when it comes down to particular conversations. And then there's also the fact that you know, it's a dynamic situation here, and you know, if you get a wire break, the effect of that wire break, of course, will shake down and will manifest itself, you know, considerable distance away from its original site. But for sure, we're quite comfortable, and when we've done measurements as a function of depth, because with the opportunity, so we do measurements at different distances away, we actually get no degradation of our signal to the extent that we're allowed due to the physical size of samples and DTRs.
Okay, we'll allow for one last question at the back.
Hello Jeff, Charlie Smith from Shell. Last time we spoke, I don't think your system had been marinized. Are you progressing with that at all?
Yes, in 2 ways, although we have spoken to your colleagues, and we were about to deploy a diver-enabled system in January 2014, but we're not, because somebody at your end decided that's not a good idea, because divers in January in the North Sea is not a good plan. So that's we're mobilizing for that, and also we've been talking with another company who is versed and skilled in ROV interfaces and all these sorts of things in terms of deployment of our equipment in a ROV deployable scanner system. I mean, you know, these people already do advanced ultrasonics in that mode, and what we're doing is talking about the interface, which is purely, it's a mechanical interface, because our probes are a bit bigger than an ultrasonic probe, so that we can deploy in the same way. Other than that, the issues are broadly similar.